we have discussed the concept of the designing of the filter, like the FIR filter and the IIR filter. We have started our discussion from the very basic definition of the digital signal processing, and we have also discussed what are the advantages and disadvantages of the DSP over the ASP. Then we have briefly described how the mathematical model of the DSP system will be developed, and we have categorized that mathematical model into the IIR form and the FIR form, or we can say auto-regressive and the moving average form. And in total, we have named that model as the ARMA model. And these models were developed in the time domain. Then we have also discussed how the developed mathematical model will be transformed into the frequency domain using the concept of the jet transform. And we have discussed what are the different possible architecture or the realization of the developed mathematical model. And then we have described the designing concept of the FIR filter and the IIR filter. Today we are just going to cover some overview related with the designing of the IIR filter, and then we discuss here the equalization, why the equalization is used here. So if we consider here the first, that is the IIR filter, then from the given mathematical model, if we see, then we find that after applying the jet transform, because the digital signal processing systems are discrete time systems, and for the purpose of the transformation, we have to use the jet transform. And after applying the jet transform, we will get here the system function, that is the Hz of the system, described by this equation, that is the summation of the Vk z power minus k divided by 1 plus k summation here the ak z to power minus k. K is from 1 to n minus 1. And here we have assumed that value of the n is greater than m here, or the m is less or equal to m here, n here. Now we can say here that there are the different possible architecture or the realizations which are possible from the given equations. If we again write here the equation, the difference equation may be written as the yn is summation of the bk's x n minus k minus ak's y n minus k here. And we have considered here the second order system. So for the second order system, the maximum value of the k will be here the 2. So we will start this one, that is the v naught xn plus b1 xn minus 1 plus b2 x minus 2 minus a1 yn minus 1 minus a2 n minus 2. And the possible structure that can be done here directly, or we can derive this architecture directly from this formula, can be described in this manner. That is, the whatever is the xn, it is delayed by 1 delay, and then it is multiplied by a coefficient b1, and without delay xn will be multiplied by the b naught. And again, if it is delayed by 1 delay, then the total delay for the xn will take place the 2 here, and it will become the x minus 2, and it is multiplied by the b2. After multiplication, here we will add these partial products with the help of the adders here. And now this will describe, this section will describe here, this section here, there is the first term, that is the b naught xn plus b1 xn minus 1 plus b2 xn minus 2. Similarly, if we are interested for the second term here, that is the minus a1 yn minus 1 minus a2 yn minus 2, then we have to select here the yn, and it is delayed by 1 delay and by 1 unit here. Then we will get here the yn minus 1, and now it has to be multiplied by the coefficient of the minus a1. Similarly, if we again introduce 1 delay, that is the y, we are now getting here the yn minus 2, and it will be multiplied by minus a2. And now we will add them in order to get the second term, that is the minus a1 yn minus 1 minus a2 yn minus 2. And now if we add these two terms, that is the first one associated with the xn, or the delayed version of the xn, and the second, that is the y delayed version of the yn, or the output, previous outputs, then we will get here the yn. Yn is a summation of these two terms here. And since this is directly derived from this equation, that's why we have named this architecture as the direct from first architecture here. Now we can reorder them. And after reordering, what will happen? If we see, then we'll find there is a series of the Z here, and there is series of the Z inverse here, that is the delayed here. Now we can change these positions, that is the first term, this is the second term, and this is the first term. We can replace each term here, that is the first will be replaced by the second, and by using the cascading concept here, then what will happen? One series of the delay is followed by the second series of the delayed, and now we can merge them, and after merging we will get this type of the architecture here. That is, now there are the total 2 delays in place of the 4 delays, and here it will be multiplied by the B0, B1 and the B2, because we can see it from the previous one, that is the V0, B1, B2, it has been shifted towards the right side, and this one has been shifted towards the left side. So by interchanging the position of these two terms, we will get here this architecture, and this is named as the direct form 2 architecture. What we have done in this one, we have reordered the feed forward and the feed back section, and now we are getting the another architecture that is named as the IIR direct form 2 architecture here. Now the implementation issues. What are the implementation issues? During the time of the implementation issues, we have to consider first, if we consider the coefficient quantization. Coefficient quantization means we have to introduce the concept of the precision, because basically during the time of the development of the mathematical model, we have assumed that we are using the infinite precision. Infinite precision means whatever is the information, the same will be implemented with the help of the parameters, and parameters will be modeled using the coefficients here, and we have assumed that the coefficients have the infinite precision. But it is not true here in the practical sense, because during the time of the implementation we have to limit the length of the coefficient here, that is the length of the bits that will be used in order to represent the value of the coefficients here. So precision usually is limited to, and that will depend upon the word size here of the processor. So it wants coefficient to be large in magnitude to use and as many significant bits as possible here. Now there are the two contradictory statements. First is for the purpose of the implementation, the number of the bits should be limited here, and second one is for the getting the exact information. Here as many number of the bits exist, we are getting more and more accurate representation here. So naturally we have to make a compromise, a trade-off between these two. And now if we are limiting the number of the bits, then what will happen? It means we are rounding the value, and the round of error will take place, and the round of error, that is the least significant bits, will be lost here. And now we have to select the different methods in order to discard the least significant bit. And what will be the effect? That it will result from big accumulator, and that is the 60 bits. If we again come to this one here, then we'll find it is nothing but this is the accumulation. Whatever is the here the coefficient, that will be multiplied by the input signal or the previous input or the previous outputs, and then this will be accumulated here. Now the result of the accumulator, that is the accumulator has word length of say 60 bits. It has to be stored back into a single word length having, for example, say the 24 bits having the 6 bits at the guard bit, etc. here. And the second is round of errors can accumulate due to the recursive feedback structure of the IIR filter, because here if we see IR filter, the first is the round of error is taking place, and the second is if we see this one or this one here architecture, then we will find whatever is the output, that has to be again considered as the input. So due to this one, that is the due to the here the recursive structure, the round of error will again be accumulated here. So these are the problems which will take place. This is the reason why we are going to quantize the coefficient, and these are the effects which will take place here. Here the due to the quantization. Now the another implementation issue is the due to the limitation of the bits, here what will happen? Overflow will take place, overflow error will take place, means most significant bits will be lost here. So it means it occurs when arithmetic result is too large to fit in accumulator or in storage word size, and overflow can linger due to here feedback also here, and it requires scaling of the input and output. In order to quantize this one, there must be a need of the scaling here. So the coefficient quantization, round off error and overflow error behavior can vary from one filter structure to another structure, or even here the results will be changed here. So results may change, or the structure may be changed, or sometimes stability may also here the suffer due to this roundup. So verify filter performance with quantized coefficient. So we have to verify whether we are in the permissible range or we are outside of the permissible range, and then assess round-off error by modeling the truncation as a noise source in the filter structure and determine the transfer function from each round-off noise source to the output. Now calculate overflow situation by looking for peaks in frequency response from input to each accumulation point in the filter here. So due to the quantization, now the errors will take place, and we have to analyze the effect of these errors. For these purposes, we have to here assess the round of errors, and we have to calculate the overflow situation due to the quantization here. Now, if we see second order section of the IIR filter, in the second order of the IIR filter, naturally there will be the two delays related with the input and two delays related to the output here. So what will happen now? Why we use the first order section and second order section? Generally implement high order IIR filters as a sum of cascade of the second order filters and the first order filters. Why? This reduces the sensitivity of the overall response to the precision of each coefficient. Here, the precision effect of each coefficient will be reduced if we are using the second order section and the first order section in place of that using the complete designing of the required order. For example, if we have to design 32nd order system, then that will be broken into the 16 sections of the second order section, and each second order filter that is named as the bipart implements two zeros and two poles that will be real or the complex conjugate here. And here the transfer function of this second order section now may be represented something like in this manner, that is the b0 plus b1 z to power minus 1 plus b2 z to power minus 2 divided by 1 plus a1 z to power minus 1 plus a2 z to power minus 2. And now we can see the architecture of these filters here. That is this is the direct form 2 and this is the direct form 1 architecture, or the realization of the second order or the bipart section of the IIR filter. Now, high order polynomials is factored to find the poles and zeros, and the poles and zeros are grouped in pairs. Usually try to group in such a way that minimizes the peak gain of each section. If it is cascaded, then second order sections are usually ordered from lowest gain to highest gain. These are the points which has to be considered during the time of the designing and during the time of the selection of the orders here, because first of all we have to break the total order into the first order section and the second order section, and then we have to arrange them. What is that one? That is the high order polynomial is factored to find the poles and zeros, and the poles and zeros are grouped in pairs. Usually try to group in such a way that minimizes peak gain of each section here. If cascading order has to be selected here, then second order sections are usually ordered from lowest gain to highest gain to minimize overflow likelihood problem here. And scaling may be needed for overall response or for each section individually, that is for the computation versus quality purposes here. Design algorithms for the continuous time filters are well known. That is the while Nyquist issues make discrete time IIR filter design. What is the concept? Concept is to use a continuous time filter design, then transform S-plane poles and zeros to the Z-plane. We have discussed the designing of the IIR filter into the S domain, and we have also discussed how we will transform this S-plane design into the Z-plane design, that is the HS, how the HS will be transformed into the HZ form. Now, what is the need? Need is an invertible mapping function between the S and Z plane is required, so that the properties or the performance of the HS may be transferred to the HZ. Now, there are the different types of the transformations. That is the j omega axis. We have to consider the j omega axis of the S plane and map it to unit circle in the Z plane. Warp frequency response will take place here. So take left half of the S plane, that is the stability region, and map to interior of the unit circle, that is the stable poles remains stable poles, and have a smooth and monotonic warping here. And that is here we describe only the customary function, that is without any coefficient. Then we can say Z is a function of the S that may be represented 1 plus S by 1 minus Z, or we can inversely represent this one, that is the S may be represented as the inverse function of the Z, that is the Z minus 1 upon Z plus 1. And now frequency warping, here the Z is e to power minus j omega, and j capital omega is the analog frequency, and small omega, this one is a digital frequency. There is a relation, that is j sin omega by 2 divided by cos omega by 2, and hence we can say it is the j tan omega by 2. That is a non-linear relation between the analog frequency and the digital frequency. Now, what is the plan? How we will make the plan? For that purpose, determine the required critical frequencies and levels in digital domain, then use the bilinear transform to find the analog specifications. That is the omega p, omega s, pass band edge frequency, stop band edge frequency, and pass band ripples, stop band ripples, etc. will be given here, and we have to determine the required critical frequencies and levels in the digital domain, and then use the bilinear transform to find the corresponding analog specification. Design the continuous time filter meeting warp specification, and then inverse transform to get the resulting digital design, and then you have to verify, then alter and repeat process as necessary here. If there is a need of the repetition, then naturally we can repeat this one. Now, for the purpose of the designing, we can use the different types of the MATLAB functions which are available in the MATLAB for the purpose of Butterworth, Chebyshev, and elliptic here. We can use the IIR table. Now, we have here in this discussion, we have just discussed what are the main points which we have to consider during the time of the designing of the IIR filter. And what are these filters? We have discussed what is the mathematical model of the IIR filter and how the transfer function of that IIR filter will be represented. And then with the help of the transfer function, we can realize here the architecture of the filter, IIR filter, and in this particular case, we have considered the second order filter here. And then in the second order, we have considered the two architecture. One is the direct form 1, and the second one is the direct form 2 architecture here. Now, implementation issues. During the time of the implementation, what is happening? During the time of the designing, we have assumed the infinite precision. means each and every coefficient will be represented using the infinite number of the bits. But during the time of the implementation, there is need of the finite word length, and for that purpose, the finite number of the bits has to be used, and that is the limited to the word size. And due to this limitation, the coefficients will be quantized here. And when we say the coefficients will be quantized, then what will happen? Now, if we again see here the mathematical model, this one here, the coefficients b naught means b case and a case are quantized here. Then what will happen? The quantization will take place at the level of the multiplication. That is, the coefficient is multiplied by the signal. That is the present signal, previous signal, or the previous output, and then it will be added to the previous result. So here the in the product quantization will take place, and in sum quantization will take place, and here the coefficients is quantized. So how many quantization are taking place? And at the same time, since we are using the finite length of the memory for the purpose of the storing the result, so input will be quantized. So how many type of the quantizations are taking place? One is the input quantization, second is coefficient quantization, third is here the product quantization, and the fourth is sum quantization, and the fifth one is the final output quantization here. Now, due to this quantization, here the round of errors will take place, and round of errors may affect here the overflow error, and there may be the round of errors, and the overflow errors behavior may take place here. And so we have to analyze the result, means we have to analyze the performance, and how the performances will be analyzed. As we have discussed in previous lectures, that during the time of the analysis of the performances, we have to see what is the time elapsed during the time of the processing or in order to implement the algorithm. And the second one is the time is related with the speed also, because the propagation delay time, processing delay, or this speed, first parameter. And the second parameter is what is the power consumption, what is the energy level required for the purpose of the implementation, the second parameter. And third one is the space, that is the space required, memory space is required, or space required on a silicon wafer. And the fourth parameter, that is what will be the effect of the quantization. Quantization means we have to use the finite word length. So due to this finite word length, now the round off will take place. So at this round off may take place in form of the overflow, or sometimes round off may again be accumulated due to the auto regression in IIR filter. So the limit cycle oscillation may take place here. So what is the effect of this quantization? That is what is the effect of the finite word length. So the fourth parameter is the finite word length effect. So during the time of the analysis, that is after quantization, we have to again analyze these four parameters. One is the speed, the second one is the power consumption, and third one is the space, and the fourth one is the finite word length effect. And now on the basis of the these performances, means what is the parameter that is related with these four parameters, either we can accept it, means if the results are satisfactory, then naturally we will move for the implementation and other purposes. Otherwise, there is a need of the modification in the model of the filter or at another level of the designing and the implementation. Now here we have also discussed the second order sections. We have discussed one concept that during the time of the implementation, whatever is the order, if the order is very high, that is greater than the second order here, then that will be broken into the first order section and the second order section. Why this larger order is broken into the first order section and the second order section? Because it reduces the sensitivity of the overall response to the precision of the each coefficient. Due to this one, we have to consider the breakup of the FOS and the SOS, first order section and the second order section. First order section will be only one section if it is the odd, and if it is the even, naturally there will be only the second order section. Second order filter, that is also named as the bicard, it implements the two zeros and the two poles, and that are the here the real are the complex conjugate. And the HZ, that is the transfer function of the system, may be represented by this equation here, that is the V naught V1 Z to the power minus 1 plus V2 Z to the power minus 2 divided by 1 plus A1 Z to the power minus 1 plus A2 Z to the power minus 2 here. And here the high order polynomial is factored to find the poles and zeros, and then that will be represented into the second order sections here. Poles and zeros are grouped in pairs, and usually we will try to group in such a way that minimizes peak gain of each section. That is, what is the peak gain that has to be minimized during the time of the grouping. And the next point is, if cascaded, then second order sections are usually ordered from lowest gain to highest gain. And what will be the effect? It will minimize the overflow likelihood. And scaling may be needed for overall response or for each section individually. For each section or for the overall designing each section means, because we are using the second order sections here, either in the cascade manner or in the parallel manner. So each section has to be scaled, or we can scale here the overall design. That is, this scaling is used for the hybridization of the computation versus the quality here, because the computation is more and more complex, the quality will be better here. But during the time of designing, we will try to make the simple computation here. So for the computation versus quality purposes, we have to use the scaling here. Now, design algorithms for continuous time filters are well known, so we will try to use the designing of the filter in the continuous time domain, and then we will transform it to the Z domain. That is the concept. So what is the concept that will be used? The concept, use a continuous time filter design, then transform S plane poles and zeros to the Z plane here. And it how the transformation will take place? Naturally, there will be a mapping is required from S plane to the Z plane, and there are the different procedures or the method that are used in order to transform the performance from the S plane to the Z plane. And these functions or these transformation method must include, the first one is, that is the j omega axis in the S plane, and that has to be mapped to unit circle in the Z plane. That is the warp frequency response. And the second one is the stability region. That is the take left half of the S plane and map to the interior of the unit circle for the stable poles remains stable poles, and have a smooth and monotonic warping. That is here the warping may be non-linear relation, then we have to consider the smooth monotonic warping here. And customary functions are like the, if we consider the Z, then Z without any coefficients, this can be set to a function of the S. Here we are not considering the coefficient for a particular type of the transformation, but we are describing it in general. That is, the Z may be represented something like in this manner, that is 1 plus S upon 1 minus S. And then inverse mapping, that is the how the S will be represented, that is the inverse function of the Z transformation, and Z minus 1 upon Z plus 1. Frequency warping, that is what is the relation between the analog frequency and the digital frequency. If the small omega, that is this one, is the digital frequency, and the capital omega, that is this, is the analog frequency, then it can be represented something like in this manner, that is the j omega is equal to j sine omega by 2 divided by cos omega by 2, that is name, and that will become here the j tan omega by 2, and this is a non-linear relation here. Now what is the plan? So during the time of the designing such filter, determine the required critical frequencies and levels in digital domain, and then use bilinear transform to find the analog specification. Now design the continuous time filter meeting word specification that has been derived in step 1, and then inverse transform to get resulting digital design. Then what will happen here? Now if due to the warping the non-linearity takes place in the first step, then that will be counterbalanced in the third step again here. And now verify, then alter and repeat process as necessary here. And we have also discussed that we can use the MATLAB function for the purpose of the computation, which we have described in these methods. So this is the method here, and we can also use the MATLAB, that is the FDA tool, for the purpose of the designing. And for that purpose, as we have discussed, that we have to open the MATLAB, and then for the purpose of the design we can use a toolbox that is named as the FDA toolbox here. FDA toolbox is filter design and the analysis toolbox, and we have also discussed that in the MATLAB there are the 3 types of the facility. One is we can write the program, or we can use the commands of the MATLAB, and now we can develop a file, that is the, we can save the file in the .m file form. Or the second one is we can use here the toolbox. In the toolbox there are the different programs related to a particular field, and these programs are arranged in such a manner that we can cover the total field. And in this one, what happens in the toolbox, when we select a toolbox, a dialog box is opened, and in these dialog box we have to put here the parameters which are required in order to design the filter, and these parameters will be calculated on the basis of the theoretical concepts here related to that particular field. So first of all, we must be aware with the theoretical concept, and with the help of these theoretical concepts we can derive here the parameters, and now these parameters may be put in the dialog box of the MATLAB toolbox, and then we can design, or we can analyze, and we can even quantize and implement our filter or the system with the help of the MATLAB. And the third step is the using the block diagram concept here. That is, whatever is the designing, that will realization will be here the described. That is, first of all we have to derive the mathematical model. Then from that mathematical model we can mathematical model in the time domain or in the transform domain, and we can draw the architecture or the realization architecture, and with the help of that block diagram we can design the filter using the MATLAB facility that is named as the Simulink, and the file, when we save the file, it is named as the .mdl file. FDA tool, as we have discussed, and we have done a lot of experiments using this one, so we are well aware with this toolbox, FDA toolbox, that is the filter design and analysis toolbox here. And when we select the FDA tool, then we will get a dialog box. This is the dialog box here. And now with the help of this dialog box, we can design our required filter. And for that purpose, we have to select the response type. And response type, as we have discussed, that first of all, we have to design the filter that is the low pass. and that low pass filter can be converted in any form which is required here. So we will select here the low pass filter, and then the next step is what is the design method. Particularly we are discussing the IIR filter, so we will move to the IIR filter. And in the IIR filter there are so many methods, approximation method like the JVC and Butterworth, JVC 2, JVC 1, elliptic, and the maximally flat, least PF norm, and constant least PF norm. So we can select any one type of the approximation method here, and we can design the filter here. Now say if we select the CVC 1, then in CVC 1 we have to describe what is the ripples or the what is the attenuation in the passband, and this attenuation is also known as the maximum attenuation in the passband. And what is the attenuation in the stop band at the F stop or the stop band is frequency, and it is at this point it is named as the minimum attenuation of the stop band. And we have to also describe here the pass band and the stop band edge frequency, that is named as the F pass or the F stop, or sometimes it is written as the FP and the FS. And here the capital F by S, capital Fs by 2, it is nothing but this is the capital Fs is the sampling frequency. So, and next section is the filter order. Here we have to describe the filter order. If from the given specification we have calculated the filter order, and that is we are especially interested for the given specification, then we have to calculate the order according to the formula of a particular type of the approximation. If we have selected the CVSAFE type 1, then using the formula of the CVSAFE type 1, we have to determine the order of the filter. And whatever is the order, that will be put here. Similarly, we can select another type of the approximation method, that is the Butterworth, CVSAFE 2, elliptic, or the any minimum least square method. Whatever is the method, that can select here. Now, the second one is the minimum order, that is for the given specification, what is the possible minimum order. For that purpose, we have to select the second option here. Now, suppose we have selected this one, but we should always calculate the order from the given specification, that is what is the pass band frequency, stop band frequency, and then what is the attenuation in the pass band, what is the attenuation in the stop band, and what is the sampling frequency. Accordingly, we have to calculate the order. Now see, if we use here the order, then in frequency specification there will be only two frequencies has to be described, Fs sampling frequency and the pass band edge frequency, because during the time of the calculation of the order we have utilized the other frequencies like the here the stop band edge frequency, etc. here. Now if we select this one, minimum order, then we have to describe all the frequencies. What is the pass band edge frequency, what is the stop band edge frequency, and what is the sampling frequency here. And then we have to also, in the next dialog box, we have to select what is the attenuation in the pass band and what is the attenuation in the stop band. In the pass band, we write the AP or the A pass. It means what is the attenuation at the pass band edge frequency. What is the attenuation at the stop band edge frequency, and the units will be described here. The units will be either in the dB or in the squared form. Now, after selecting this one, as we know, we have to design the filter, and we will design it. So, what we are doing here, from the given specification, we have determined the parameters and the values, and those values are the parameters are put here in the dialog box for the purpose of the designing of the filter. Now this software or the toolbox will compute all the coefficient and draw the graph as per the mathematical description whatever we have described in our previous lectures here. Now suppose we have described this one, designing has been completed, then we have to analyze whether the performance is within the here the permissible range or it is outside of the permissible range. So for that, now see here, the the filter that has been designed, it is a direct form FIR filter, and the order is 50. It is stable, yes. The source is designed here, and during the time of the analysis, we have to analyze these. Here the parameters, that is what is the magnitude response, phase response, magnitude and phase, group delay, phase delay, impulse response, step response, pole zero plot, filter coefficient, filter information means that is given order, etc. Here magnitude, response estimate, round of noise, power spectrum round of noise is related to the quantization effect here. So these are the different procedures which has to be used for the purpose of the designing. And after designing, the next step is this one, that is the quantization. For the before the implementation, we have to quantize the coefficient here. Now, for the purpose of the quantization, you have to select a particular type of the number system. For example, we have selected the floating point number system, and that is the double precision. When we say double precision, that is a 64-bit per length. So, infinite number length, infinite number of the bits now will be truncated by the 64 number of the bits here. And then we will select here, or we can say another type of the, that is the single precision, or say fixed point. So there are the different types of the numbers representation. As we know, there are the two broad categories. One is the fixed point representation, and the second one is the floating point number system here. In the fixed point, say fixed point, we have to use the here the different format, that is the qm.n form, and the in double precision floating point we have to use the 64-bit, and in the single precision floating point we have to use the 32 point, and these are the IEEE 754 standard here. See, these are the responses. One is without the quantization, and the second one is the with the quantization here. So we can see here the responses after the quantization here. Now say, suppose we are interested in order to realize the model, then for the purpose of the realization, we have, as we have discussed in the IR case, the same can be done here also. That is, we can use here the basic building block for the purpose of the designing. And after selecting this one, here realize the model. Realize the model means now the architecture will be developed here. And here we can see what are the number of the adders, multipliers, and the memory devices here, because we have selected here the basic building blocks. Or we can also select here the override and generated filter block, that is the total filter will be represented with a block here. And we can give the input, and we can see what will be the response or what will be the output here. So here in this lecture we have discussed the what is the mathematical model, what is of the FIR filter, and what is the corresponding transfer function architecture, and then we have also discussed here the quantization and the effect of the quantization, and we have also discussed the designing concept of the FIR filter. That is, we have tried to sum up the concepts of the IIR filter design, analysis, quantization, and the implementation. See here, I think we are in this one, realizing the model. So as realizing will take place here. So after this one, after realizing, we can see here what is the architecture of the IIR filter. Whether people have any doubt, other questions from the student side? See, this is the here the architecture, and in this one we are using the direct form 1 and the direct form 2 realizations. Theoretically, we have described the architecture of the direct form 1 and the direct form 2 of the FIR filter. Now we will see what is the architecture and that has been computed with the help of this software, that is the MATLAB. And that is also a direct form FIR filter. Now see, this is the block of your filter which we have selected here. And what is the specification? The specifications are given in the during the time of the designing using the concept of the FDAR. So if we are interested in order to see the architecture of this filter, then you just double click on this one here and you will see the architecture. Now see here the input is given, and then these are the coefficients here, that is the B1 and B2 etc. here, and these are connected here in this form. And the next one is related to the B1, B2, B3 up to, see here, 37, 39, 40, 40. B51. The order is 50 here. So these are the this is the architecture of the filter which we have designed. Now we can also see here what are the values of this coefficient. And for that purpose, in the analysis menu, we can see here the filter coefficients. Then we will find the values of these coefficients here. So this is and filter information is this one, that is the filter structure is direct from FIR. The filter length is 51, order is 50, stable yes, the linear phase yes, and among the linear phase there are the 4 categories, type 1, 2, 3 and 4, and this is the type 1, and the arithmetic which we have used is the phase, numerator and input. These are the different values which are given here. And we can see the implementation cost, that is what is the number of, what are the number of the multipliers, adders, states, and these are how many number of the multiplication will take place, number of additions will take place. These are described, that is the complexity has been described here in order to decide the implementation cost. So this is about the designing of the IIR filter which we have discussed here. We have discussed the summary of the designing of the IIR filter, mathematical modeling of the IIR filter, realization of the IIR filter, design, analysis, quantization and implementation of the IIR filter. So this is about the today's lecture. If you people has any problem,